So latency analysis is great, and that's when I can really understand the effect of the file system on applications. Here I show the different layers you can target and their pros and cons. I may do file system latency analysis in the application. Pros, it's closest to the measure of the effect on file system latency, and we can inspect application context. And so I might find that, yes, this file system latency happened during a MySQL query, therefore it is slowing down the MySQL query. Or I may find this file system operation happened during this application asynchronous thread that was just doing housekeeping. It did slow down the application, but we don't care because it's a low priority thread. And so that's the best measure of the effect on the application. The cons, technique varies between applications. You need to know application internals. So it's not a generic manner. It requires quite a bit of digging. If you do it from the syscall interface, pros, well documented, commonly observable via operating system tools. With dtrace, it's the syscall provider. Cons, syscalls catch all file system types, including non-storage file systems like statistics and sockets, which may be confusing, so you need to filter them out. There may also be multiple system calls for the same function, like read, pread, read64. So syscall tracing, fantastic, I love it. There's just a couple of caveats to know about. So you will run into socket syscalls when you're trying to look at the ZFS one, so filter them off. And also remember to trace all the types. VFS level is interesting. That's in the kernel. That's the common API. And then you could go into the file system itself. And the advantage there is I can inspect internal file system context if I need to. Now, there's an example of looking at the, if I'm measuring it from the application level or from the syscall level, I get to see as close as possible to the full latency that the application suffered. Within the kernel, that file system I/O may have an on-CPU component. Like I might go to the ARC hash locks, it does a bit of spinning, grabs the lock, realizes it's not in the ARC. Now it has to issue a disk I/O. And now we're blocked off CPU and we're doing the disk. Which is not what I'm showing here in this diagram at all. I'm showing something else. What I just said makes sense, but here I wanted to actually show where the read syscall was. So this diagram can be used in more than one way. So forget what I just said. This is actually showing not an application file system operation, but the entire application transaction. So here's where my MySQL query starts. Here's where my MySQL query ends. This on CPU work includes the inside MySQL, I'm preparing a query, I'm doing whatever stuff I need to do. Then I go into the file system and then I might be doing an ARC hash lock. And now I actually context switch off CPU to wait for the disk I/O. So I did draw this diagram to show if you're doing syscall-based tracing, that's pretty good. I should extend that a little bit, actually. Yeah, sorry, we don't go into the file system yet. We go into the file system after the read syscall is issued. So that dash needs to be... Anyway, maybe I'm getting... This is supposed to be a simple diagram, and I might be making it too complicated. So in general, it's just showing that for any application transaction, you'll have on-CPU work, off-CPU work. That off-CPU work would largely be... if it's for the file system, then I'm off CPU, I'm in a read or something. Maybe I'll update that diagram for the next version and make it more complicated, but I think it's actually trying to be simple.